Hello and welcome to this video on elastic and inelastic collisions, which is part of the Forces and Motion module in OCR A-Level Physics in the subtopic of Newton's law and momentum. So if we've been successful and we've learned in today's lesson, we should be able to define and describe the conservation of momentum, define elastic and inelastic collisions, and calculate values in inelastic and elastic collisions. So we're going to be looking at the following part of the OCR A-Level Physics specification: collisions, in particular perfectly elastic and inelastic collisions. Now, when objects in a system interact or collide, they can transfer two quantities, momentum and kinetic energy. Now, momentum is always conserved in all collisions. This is because there is nothing else into which momentum can be converted to. But kinetic energy is not usually conserved in a collision because it can be transformed into other forms of energy. Now, work can be done to form an object in collisions or be transferred to the internal energy of the surroundings in things such as heat or sound. Now, of course, the total amount of energy remains constant, as prescribed by the principle of the conservation of energy. So this leads to two types of collisions: elastic collisions and inelastic collisions. Now, elastic collisions are when the total momentum and total kinetic energy is conserved in a collision. Now, elastic collisions are collisions where no energy is lost to the internal energy of the surroundings. It is a closed system. Now, inelastic collisions are when the total momentum is conserved, but the total kinetic energy is not conserved in a collision. So you can see in the following table that if something is perfectly elastic, momentum is conserved, the total energy is conserved, and the total kinetic energy is conserved. But in an inelastic collision, whilst the momentum and the total energy are conserved, the total kinetic energy is not conserved. So to find out whether a collision is elastic or inelastic, you must compare the kinetic energy before and after the collision. Now, in reality, there are no true elastic collisions which occur in the universe. However, the collisions between particles can be considered elastic, and the low-speed collisions between objects which cause no damage can be considered elastic. An example of this can be snooker balls hitting each other. Another example of this can be a low-speed car crash. Now, in a high-speed collision of two cars, the kinetic energy could be completely transformed as the cars crumple and deform, leading to an inelastic collision. So, in an elastic collision, all of the kinetic energy is conserved, and the kinetic energy depends on the speed of the object. So this allows us to determine that in a perfectly elastic collision, such as a head-on collision, the relative speed of approach will equal the relative speed of separation. Now, in an inelastic collision is one where kinetic energy is not conserved. The kinetic energy is transferred to other stores. So inelastic collisions occur when two objects collide and they crumple and deform. Now, all the kinetic energy of the system may be transferred away from the system and the object can come to a halt, or it may be that some of the kinetic energy of the system may be transferred away and the objects will move as one body at a speed slower than the original objects. So in theory, a perfectly inelastic collision is when two objects will stick together after the collision. So let's have a look at an example of a question. An object of mass 8,000 kilograms is moving at 3 meters per second and collides with a stationary object of mass 5,000 kilograms. The objects separate after the collision. The 8,000 kilogram object moves at the speed of 1 meter per second. The 5,000 kilogram object also moves. Calculate the loss of kinetic energy in the collision. So it's obviously an inelastic collision because the kinetic energy is being lost. So the first thing you need to do is work out the term that is missing, which is the velocity of the 5,000 kilogram mass after the collision. So we can use the conservation of momentum. We can say that momentum before equals momentum afterwards. So it's 8,000 times by 3 plus 5,000 times by 0 equals 8,000 times by 1 plus 5,000 times by v. We can work that through, and therefore we can work out that v is equal to 3.2 meters per second. We can then use the kinetic energy equation of a half mv squared to work out the kinetic energy before, which is a half times by 8,000 times by 3 squared, plus a half times by 5,000 times by 0 squared, which is 36,000 joules, and then work out the kinetic energy afterwards. A half times by 8,000 times by 1 squared, plus a half times by 5,000 times by 3.2 squared, which is 29,600. We can then compare the two values and say our energy loss is equal to 36,000 minus 29,600, so it's 6,400 joules. So that brings an end to our lesson today on perfectly elastic and inelastic collisions. So if we've been successful and we've learnt in today's lesson, we can define and describe the conservation of momentum, define elastic and inelastic collisions, and then calculate values in elastic and inelastic collisions. So thank you for watching this lesson on elastic and inelastic collisions, which is part of the Newton's laws and momentum subtopic in the module of forces and motion. Thank you very much and have a lovely day.